introduction. It's a pleasure. It's an honor to be here. MagLab always feel like home because when I was a postdoc, I come here a lot. I can walk down the hallway and recognize everybody, and that's almost 10 years ago. So now I don't really get back to do experiment much more just because I don't have the opportunity, but I get to come back and tell you about all the cool physics, right? So I'll talk about bilayer exciton and quantum condensate, but let me go down the memory lane quickly. During one of my last visit here, because I visit here so often, during one of my last visit as a postdoc, MagLab sent a photographer to shadow me for a week. And so during the between experiment, they asked me to, pose on top of magnet, or sometimes they just, hang around when we're analyzing data. I don't remember what data I was analyzing, but you can see I was very happy, right? And that's part of the reason that MagLab feel like home, because every time I come here, I get to do some really cool physics, right? So after years of training, this place feels wonderful to me. So this is one of the last data set I took. I will tell you a little bit about the physics in a little bit, but so I remember this happened in the late night. When you come to MagLab to do experiment, they have to convert a lot of energy into the magnet. So a lot of the cool physics happen around midnight. I remember sitting there and watching this curve going up and down. We're tracking these dips, right? And we expect the dips to happen at certain places. And when it goes from here to there, all the dips are happening exactly at where it's supposed to be. I remember the feeling was, wow, this is really cool. Since I'm giving the talk here, let me also highlight that this data set happened at 31.4 Tesla, right? So you're required to go to one of the, I think this is cell 9, and we have to charge the magnet to the full field. This is probably second to the last day. We have this much energy, let's all dump it into a really nice data set, right? So
let me add, this was figure 1, the last row. I was looking at the magnet.
Oh, nice. Fantastic. I'm going to talk about this a little more.
I found it.
Okay, you guys should invite me back more. Right, so the point I want to make is that usually when quantum material is happening, the first version of the device is usually not the cleanest, right? So you really need the help of high magnetic field to see these features. See, in this case, these are two-component fractional quantum Hall effect, and we get to this field to get all the features. And as I go through my talk, you will see that as we start to make device better, sample becomes cleaner, the magnetic field that needed to do these become lower, right? I think this is the biggest real MagLab place that when we start to figure out how to make these quantum materials, MagLab is the biggest help, because that allow us to figure out what physics is there by going to a really high magnetic field, right? And then we know what this is a direction we can go. And then over the years, we work to reduce this magnetic field to very low. And in some cases, it's zero magnetic field, right? In this case, I'm always going to talk about measurement that's done with a non-zero magnetic field, even though that hopefully one day we can reduce the magnetic field to be zero. Okay, so the talk is structured in 3 sections. I will give you an introduction of exciton superfluid. This is something that people have been doing for many, many years. This is where I started when I was a postdoc. And then I'll go into two-component fractional quantum Hall effect and fractional excitons. I'll explain what they are, right? These are the more exotic features that come out when we start to be able to make our sample cleaner. And at the last, I'll talk about exciton solid, which is kind of an exotic concept that it's kind of also a work in progress. Okay, so bosonic condensate everybody should be very familiar with this concept, right? When you have a system of bosons, if you can cool the system to low enough temperature, there will be a boson-einstein condensate. There are lots of examples of this that we study in history. For example, when you have a helium-4 is a boson, right? When you cool helium-4 down to 2.2 Kelvin, it becomes a superfluid, right? The superfluid component of the liquid can flow without viscosity, which is a direct manifestation of the condensate. And also, in AMO systems, if you have a cloud of bosonic gas and you cool it down to microkelvin temperature, they start to, in the momentum space, they start to occupy the same state, right? That's a more direct manifestation of bosonic condensation. The talk here is more relevant to engineer bosonic condensate. This is motivated by the discovery of superconductivity, or by the BCS model, right? Everybody knows superconductivity. That probably doesn't require any introduction. So superconductivity intrinsically is a bosonic condensate of a fermionic system, right? And the way you get it to condense is to form Cooper pair. When you pair two fermions, right, you get a composite boson. So after BCS theory figure out this mechanism, people start to think about a different type of bosonic condensate, right? So this is the proposal that came out in 1975, where they talk about the feasibility of superfluidity of paired spatially separated electrons and holes, right, as a new type of superconductivity mechanism. The idea is this: you take any solid state material, you have a Fermi surface in a small band gap, right? When electron is excited from valence band to the conduction band, you get a free electron here and a hole there, right? They have opposite charge, so if you have Coulomb attraction, they can pair and form exciton. This exciton is a composite boson, right? So in principle, if you can cool the system to low enough temperature, there could be a bosonic condensate, and this is a direct analog of superconductivity, even though there are some subtle differences. But there are a few issues for getting to the excitonic condensate. If you just go into any StatMech textbook, right, that give you the formula describing the critical temperature of a bosonic condensate, is directly proportional to density, right? Which means that if you want to observe a bosonic condensate at a TC at a temperature that's experimentally accessible, you need the bosonic density to be high enough, right? This equation is not directly applicable to 2D system. This is a 3D equation, but I think the message is the same. So the issue is this: you want to form excitons, and you also want exciton to have really large density of state, right? And exciton usually forms at the edge of the band, which means that you want the band to be really flat, right? That will give you enough density of excitons so that you can observe the condensate at high enough temperature. Of course, there's another issue that in this picture, the electron and hole, they occupy different energy band, but they coexist in the same physical space, right? So there's nothing that stops the electron from jumping back to the valence band and recombine with the hole, which means that the exciton lifetime is really, really short, right? Which puts extra constraint for you to observe the condensation. And then, of course, there's a more practical issue that electron and hole, when they combine, right, this composite boson is overall charge neutral. And we rely very heavily on electrical transport measurement to detect quantum phenomenon, which means that this condensate will be an insulator, right? You cannot really do transport measurement, electrical transport measurement, to detect the dissipationless mass flow, which is inconvenient, right? And it turned out that all of these challenges can be fixed using a fairly easy method. When I say easy, that's in hindsight, right? It took decades of development. Alan McDonald, Jim Eisenstein, and Greg here, for example, they did a lot of groundwork to figure out this is the way to go. And the solution is a quantum Hall bilayer. You take two 2D electron gas, right? You put them really close to each other, but prevent them from tunneling. You put electron in one layer and hole in the other layer, right? These are stable electron and holes, and if you can get them to pair and form exciton, the lifetime is infinitely long, right? Because they cannot tunnel, okay? And so the schematic looks like this, right? You get two of these energy bands, and you just put Fermi energy into the conduction band in one layer and the valence band in the other layer, right? And then get them to pair, and these are spatially separate electrons and holes, right? And to address the density of state issue, right? Of course, you can just make this band extremely flat. That will require you to get two layers of exotic material run by hydro twisted bilayer, which is doable, but right now still a challenge. There's an easier solution where you get 2D electron, you just need to apply a outer plane magnetic field, right? Then you get these Landau level forming across each layer. Regardless of how dispersive the original band is, once you have Landau level, dispersion goes away, right? So you can get infinite amount of density of state that's determined by how big of a magnetic field you're applying, right? So in this situation, all we need to do is to put one layer at 1/2 filling, the other layer also at 1/2 filling, right? And if there's very strong interlayer coupling, then the electron on one layer will misalign with the electron on the other layer, right? In other words, that electron here is always aligned with the hole in the other layer, right? The ground state here is described by this wave function that this is a Halpern wave function. And in this case, the L, N, and N should all take value of 1. So we typically call this the 1-1-1 state. There's a very easy way to understand this wave function. You create a integer quantum Hall effect at filling 1 in one layer, right? And then you spread this wave function out to 2 layers evenly, right? So if you just count the electron and ignore the layer degrees of freedom, this is exactly the same as integer quantum Hall effect at filling 1. You spread it out to 2 layers, right? Then you get some kind of interlayer correlation. To see where this goes, right, all you need to do is to do a particle hole transformation on the bottom layer. Instead of looking at electron, we just look at hole, right? So what the state does is that electron on one layer is always aligned with hole on the other layer. It's like there's exon pairing, right? And at low enough temperature, this will give you a condensate phase. Okay, so experimentally, right, in this picture, I'm just showing you 2 layers of electron without any structure. Experimentally, we realized this by doing a quantum Hall graph in bilayer structure. The most important part is 2 monolayer graphing that's separated by a hexagonal boron nitride that's about 2 to 3 nanometer, right? So hexagonal boron nitride is what we call white graphing. It has the same lattice, almost the same lattice structure, but it's completely insulating. At about 2.2 or 3 nanometer, this boron nitride is still fully insulating, meaning that there's no tunneling, right? So this allows us to bring these 2 layers of electron very close to each other, allow the interlayer Coulomb interaction to do the work, right? There are some other structures. This entire core part of the device need to be encapsulated by boron nitride to ensure that the device is clean. And at the top and bottom, we add 2 graphite. These are the gate electrode, which means that we can fully control the charge carrier density in the top and bottom layer independently, right? So when you're in a Landau level, the filling of this layer we usually call nu1. Filling of this layer is called nu2, and we can control them independently, which means that we're dealing with the 2-dimensional phase space, right? And we're going to go into this phase space little by little. Yeah.
Well, in the previous slide, you showed this misalignment from the wave function. So, like this misalignment, the way how do you do it? Is this a picture or?
I think you can see that from the wave function. That's a great question. And maybe let me get back to you, because I'm going to have to stare at this for a while before I can answer that. Or we can just turn to Liang or Oscar, who can just answer it for us. Right. When you have this structure, right, you still need to make a decision on what kind of device to make before you do transport measurement. Usually there are 2 options, right? We can pattern each layer into a square shape, and we call this double Hall bar, right? Each layer function as a Hall bar. You flow current, you can measure longitudinal transverse resistance. Another option is what we call double Corbinal, that we pattern each layer into this donut shape, annulus shape, where the advantage here is that when you flow current from the outer edge to the inner edge, there's no edge transport, right? So you directly probe bulk conductance. It turned out that this one is much more advantageous, but I'm going to talk about both configuration. Okay, so when each layer is at 1/2 filling, we are supposed to get this exciton condensate ground state at low enough temperature. right? And so what is the transport signature of such a condensate phase? So if you take the double hole bar sample geometry, where each layer is a square, right? One type of measurement you can do is called counterflow drag, where you flow current from the top layer, left to right, and the bottom layer is passive. There's no active current flow, you just ground it, right? And then you can measure the transverse resistance across both layer and also longitudinal resistance across both layer, right? So this can probe one very unique feature. When you have exciton condensation, the two layers are coupled together, right? And because you're in the quantum Hall effect regime, there has to be an edge channel. Because the two layers are coupled, this edge channel actually lives on both layers at the same time. We call this, or Jim Eisenstein called this, which layer uncertainty, right? So what happens is that when you inject current on the top layer, there's an edge mode that flow on both layers at the same time, even though the bottom layer is completely electrically passive, right? And then that shows up as this measurement. Total filling of -1, that's when each layer is at half filling. This is where we expect the exciton condensate to appear. The bottom panel is plotting transverse resistance measured from the active layer and the passive layer, right? And you can see that both layers show a quantization at 1, meaning that there's a single edge channel that shares the two layers at the same time, right? And when current flows along this edge channel, longitudinal resistance drops to 0 for both the passive and active layer, meaning that the exciton is flowing dissipationless, right? Or you can also do this in a slightly more straightforward way. You flow current from left to right on the top layer, and you just feed it back and flow the current in the opposite direction, right? The advantage here is that because the exciton has opposite charge electron hole, when you flow current in the opposite direction, you're actually moving the exciton on its own, right? And when you look at the transport response, exciton is overall charge neutral, so it does not experience any Lorentz force, right? And when you flow exciton in the bulk, the transverse resistance in this configuration is 0, meaning that what carries current is something that's overall charge neutral, right? And at the same time, longitudinal resistance is also 0, meaning that when exciton flows, it flows dissipationlessly, right? If you park your sample right at this point and change temperature, right, you can see this very sharp transition that just looks like a superconductor. If I just show you this data, right, without telling you what it is, you'll say, oh, that's a superconductor, right? So there's some similarity. The one thing I guess I forgot to put here, this is measured at, I think, 35 Tesla, right? This is one of our early experiments. In order to stabilize this exciton condensate very robustly and get this very sharp transition, we have to go to very high magnetic field. And we utilize the series connected hybrid magnet in cell 14. And I think we're one of the first users. We're definitely the first transport users on that magnet.
That's thinking about the excitons as a storm space and solve the electronic like how do I think about the current at the end? That is like the particles current the exit.
Right. You can think of a electron hole being when we flow current here. Let's say we're injecting electron here, and we're injecting holes here, right? And then they move together to this side and they annihilate together. You can think of it that way. Okay. So let me focus on the Corbino geometry, right? With the Corbino geometry, I identified the outer and inner edge of the top layer as 1 and 2, right? And 3 and 4 is those two of the bottom two layer. And there are 3 different ways we can measure this, right? We can flow current in the same direction across top and bottom layer at this exciton condensate state. Because exciton is overall charge neutral, when you try to flow current in the same direction, you will not flow, right? You will behave as an insulator. And so here I'm plotting conductance in this parallel flow configuration. So PF means parallel flow as a function of total filling at total filling of 1, meaning each layer is half filling, right? You see this insulator. And if I were to do the counterflow, meaning I flow current from 1 to 2 and then loop it back from 4 to 3, right? Then suddenly at this insulator, I start to see a very large counterflow conductance, meaning that there is something that's overall charge neutral that's flowing, right? The downside of the Corbino geometry is that this is a two-terminal measurement. So even though this is the condensate phase, I still measure the conductance does not diverge, right? That's the price we pay. But most interestingly, you can do this so-called current drag measurement that you form a circuit across the top layer, right? You drive a current across the top layer, and then you just measure how much current flows in the bottom layer, right? So you can, on here, I'm plotting I drag versus I drive. And at this condensate phase, you see that it shows a perfect drag ratio, meaning that a excellent condensate performs as a perfect transformer in this geometry, right? So one thing I should note that all these measurements are performed at 1 Tesla, right? That shows you kind of, this is a measurement we did, I think 1 or 2 years ago. Yeah.
So for this drag,
Yeah.
if there's a load resistance in the bottom circuit,
Yeah.
that's the time you by the off circuit and then power the load.
Yes. It's as if you are adding a load directly to this circuit, right? Because the alternative, right? The alternative is it only flows as exciton. There's no other charge that's willing to flow in this case, right? And also the reason that we can only do this with the Corbino geometry, if you try to do this with the whole bar, right? On the drag layer, there's always an edge state that's dissipationless. So if you try to do this with the whole bar, you cannot add a meter to the edge channel, right? The only way to do this is to decouple the edge channel so that you directly look at the bulk. You're able to start to see this. And let me also mention that we're not the one who figured out the Corbino geometry. Jim Eisenstein did this more than 10 years ago. But the point here is that the Corbino geometry seems to allow us to stabilize exciton condensate at a magnetic field that's much, much lower than the whole bar geometry, right? So, which means that if we take this geometry to go to higher magnetic field, then there's a chance we see something new, right? Okay, so great.
Today you state that today what might not use on this thing that I think that so what the inside thing.
What determines the width of any quantum hole plateau disorder, I think. Yeah. Okay, so let me move on to the second part to talk about two-component fractional quantum Hall effect and fractional excitons. Right. This is important because that you're taking two layers of graphene and you're applying a really large magnetic field, right? And so fractional quantum Hall effect is a part of the physics that you just cannot avoid. So let me first go into fractional quantum Hall effect in monolayer graphene. You guys have already heard a lot about composite fermion model. But I think for the purpose of this talk, it's still necessary for me to go into it a little bit. This is a bulk measurement conducting monolayer graphene that's patterned into a single Corbino geometry, right? So the y-axis here is bulk conductance. When you have a fractional quantum Hall effect, there's a charge gap developing, which means that the ground stays incompressible. In the Corbino geometry, then it will show up as an insulator because there's no free charge. To excite quasi-particle, you have to overcome a really large energy gap, right? So at low enough temperature, it's just insulating. So when I plot between 0 and 1 Landau level filling, all of in between is fractionally filled Landau level, right? So the fact that you see all these insulating state developing means that there's some kind of correlation-driven effect, right? So to understand these fractional quantum Hall effect, I have a very hand-wavy picture that you have a 2D plane and you apply a magnetic field, right? Let's assume the magnetic field equals 9 flux quantum, right? That means that the Landau level has a degeneracy of 9. You can host 9 electrons, right? For example, you can put electron in 2 Landau orbital. In this case, the filling fraction is 2/9, right? And now you allow electrons to interact with each other strongly through Coulomb interaction. The consequence of that is that whenever you have electron occupying 1 Landau orbital, the adjacent orbital becomes energetically unfavorable, right? So if you put electron here, then you really don't want to put electron in the adjacent to lambda orbital. The way to model that is to just take out the magnetic flux. You take away the flux, you attach to the electron, right? These two lambda orbital goes away. And the consequence of that is that the filling fraction of this lambda level goes from 1/9 to 1/7, right? And so with this method, this is two flux attachment. With this method, you can calculate the effective filling of composite fermion by taking away the flux attached to electrons, right? If you plug in phi equals 2 and mu equals 1/3, you realize you get an effective filling of 1, right? So according to this picture, all of these fractional quantum Hall effect, you can calculate their effective filling. You realize that fractional quantum Hall effect is just effective integer quantum Hall effect of composite fermions, right? And as the filling fraction goes higher, the effective magnetic field becomes lower, then the energy gap becomes weaker, right? That gives you the hierarchical behavior of 1/3 being strongest. As you approach 1/2, the state becomes weaker and weaker, right? So that's the story of a single monolayer graphene. Now we can add the layer degrees of freedom, right? Instead of one layer, now we have two layers. When you put electron into the system, they can either go to the upper layer or the lower layer. It's effectively very comparable to spin picture. You can put electron with spin up or spin down, right? So we know that a lambda level filling on the upper layer as nu up, nu down. In a lot of literature, people also refer to the layer degrees of freedom as pseudo-spin degrees of freedom, right? Because they're extremely comparable. Okay, so how do we account for strong interlayer interaction, right? If you have electron in both layers and they interact extremely strongly, what happens is that when you have electron in one lambda orbital on the upper layer, this lambda orbital becomes inaccessible, right? You have to pay a really large Coulomb price. So in the composite fermion picture, to do that, you just take away this flux, attach it to the electron on the opposite layer, right? We call this interlayer flux attachment. So this creates a different type of composite fermion, which is supposed to give rise to a different type of fractional quantum Hall effect sequence we call two-component sequence, right? And you can calculate the sequence using this equation. The effective filling now depends on the filling fraction of both layers, right? Because you have interlayer flux attachment. And this is going to change the fractional quantum Hall effect sequence completely. For example, when you take A equals 2, two interlayer flux attachment, one interlayer flux attachment, and you put each layer to be 1/4 filling, total filling equals 1/2, right? Effective filling is 1. So this is one of the strongest interlayer fractional quantum Hall effect state that happen at even denominator film, which does not occur trivially in a single layer system, right? So to just summarize, this is the fractional quantum Hall effect sequence in a single layer, and this is the fractional quantum Hall effect sequence in a two-layer system, right? And we're measuring along a line where the filling fraction of the two layers is always the same. We call this the equal density line, right? So you can spot lots of differences. For example, at 1/2 filling in a monolayer, it's conductive, but 1/2 filling in the two-layer, it's the strongest incompressible state, right? This is the exciton condensate that we just talked about. And if you look at the filling fraction, there are lots of even denominator fillings in this system, right? And all of these can be accounted for by a 2+1 composite fermion construction. The effective filling is noted at the top. It's either integer effective filling or half integer effective filling, right? The half integer probably indicates there's some kind of pairing between the composite fermions, which is a very exotic consequence of the two-layer system. So we were doing this experiment around, I think, 2017, and we were using this composite fermion model to figure out that we need to attach an interlayer flux to explain all of these. And as we were doing these analysis and feeling really good about ourselves, we realized that Jinendra already wrote a book 20 years ago about composite fermion. There's many chapters I read many times, but there's a chapter 14 at the very end. He talked about when you have two species of electrons, you can have interspecies flux attachment, right? So I guess then the way to spin the story in a very positive way is that Jinendra predicted something many years ago and we observed it the first time, which is still very cool. Okay, the one thing that Jinendra, I guess, did not fully anticipate is that in this system, we have a two-dimensional phase space, right? We can control nu1, nu2 independently, which means that the measurement we're doing or we're supposed to do, at least, is not a line. It should be a map, right? So let me show you the map first. This is the map. I'm doing parallel flow measurement, right? I'm plotting parallel flow conductance. Dark blue means that it's fully insulating, that there's an incompressible state, right? And the red and dark red means that it's highly conductive. It's a compressible state. The map is x-axis total filling, right? At total filling equals 1, there's a vertical feature. This is the 111 state. This is the exciton condensate. The reason that it's fully developed along this line is because if you have a system of excitons, if you flip one exciton upside down, you still have a system of excitons, right? Flipping exciton is changing the layer imbalance, delta nu, right? That's the y-axis. Okay, and away from this exciton condensate, you can see that there's a number of different things happening, and this becomes quite complicated. But the way to understand this is also very straightforward. If you look at two-component fractional quantum Hall effect, right, there's effective filling of both layers that depends on the flux you're attaching. In this case, let's only consider attaching 2 intralayer flux and different number of interlayer flux, right? Combining these two equations together, you are actually looking at a map. So when you have 0 interlayer flux attachment, fractional quantum Hall effect should develop along these lines, right? At the crossing point of each line, the entire system is insulating, right? So if there's no interlayer flux attachment, you will see a pattern that looks somewhat like this. And when you start to increase interlayer correlation, fractional quantum Hall effect or composite fermions start to acquire interlayer flux, and the patterns start to evolve, right? Instead of a square, it start to become some kind of squashed diamond. And with 2 interlayer flux attachment, it becomes something like a vertical line. It's like a replica of the 111 state, right? So let me just show this comparison quickly. If we note these incompressible states, we mark their position here, right? You actually can see all kinds of composite fermion. Right next to the exciton condensate, this square corresponds to 2 plus 0 composite fermion. That's the conventional composite fermion Jane proposed. And there's this squash diamond, right? That's the 2 plus 1 composite fermion. And there's a bunch of these vertical states. That's the 2 plus 2 composite fermion, right? This is a little complicated, and for the purpose of the talk, let me not get into it too much, but let me just show you one example of creating excitons in the presence of fractional quantum Hall effect, right? We call this doping exciton into the Jane sequence of fractional quantum Hall effect. The first example I give is that I put layer 1 to be 0 filling, right? There's no electron on the top layer, and we start to change the filling of the bottom layer, right? And then you see this fractional quantum Hall effect start to develop in the parallel flow channel, which looks exactly the same as the fractional quantum Hall effect in the monolayer, right? There's they correspond to effective filling 1, 2, 3, 4 of the 2 plus 0 composite fermion. And you know that this is a single layer state because that it doesn't show any counterflow conductance, because the other layer is, one of the layers fully insulating, right? When you try to flow current in the counterflow geometry, you get an insulating response, and there's no drag. I have to grade this out because here we're doing 0 divided by 0, right? It's 0 current in drive layer, 0 current in the drag layer. Okay, and the next thing we're gonna do is to move some electron around, right? We're starting with this situation where electron is all at the bottom layer, and these electrons start to form these fractional quantum Hall effect state, right? And we're going to start to move electron from the bottom layer to top layer just a little bit. And what happens there, effectively, you're adding exciton in the system, right? You're creating this exciton in a ground state of fractional quantum Hall effect. That's single layer in nature. And this is the data, right? In this case, nu 1 0, and here we increase nu 1 just a little bit, 0.08, to fill about 10% of the lambda level, right? And we're sweeping total filling across the two layers. And in the parallel flow channel, you see all these same state forming, right? That looks identical to this. But now you start to see counterflow starting to form peaks when parallel flow is 0, right? If you plot the drag measurement at each of these fractional quantum Hall effects, say you start to see perfect drag response, right? Yeah.
So the excitons here are, they're not condensed, right? Or is that not?
Right.
This doesn't play. I'm just wondering.
Yeah.
Earlier you mentioned that
right.
you had a two-terminal.
Yeah. Right. Right. So this is two-terminal, which means that we don't know whether or not it's condensed yet. It could be condensed. We just don't know. Right. But let me just mention this one state, right? Total filling equals 1/3. We're starting to add some, both layers have some electron, right? The wave function for this actually is also understood long ago. It's the same wave function, but you take L, M, and N to be 3. So it's a 3-3-3 state. And the wave function essentially is a Laughlin wave function, and you just spread it out across two layers, right? That's exactly how we constructed it. We constructed a Laughlin state, and we spread it out a little bit, and it shows excitonic behavior, right? This 3-3-3 state was predicted a long time ago by Xiaogang when he actually predicted that this works for any numbers, 555, 777, and I think those are essentially these sequence of state that shows up.
Every session, this wave function does it have the glowing order? Is that kind of?
Yes. Yeah, it does. The title of the paper is Neutral Superfluid, and the long-range order comes from, I shouldn't get into the theoretical detail too much, but Xiaogang went through the argument that this should have long-range order. Right. Okay, so this is an example, right, that you could get exciton pairing in the presence of a fractional quantum Hall effect. And the picture is fairly rich here, as you see that there's a very big map. Let me just highlight one type of exciton pairing. I think that's quite interesting. When you have a single layer state, when you have fractional quantum Hall effect in a single layer, the 1/3 state is really well understood, right? The wave function is originally proposed by Laughlin, so we sometimes just call it the Laughlin state. It's really well understood, also in the sense that we know when you start to add excitation in the system, it's not electrons, but it's 1/3 charged quasi-particles, right? So this kind of motivates us to ask the question, would you be able to form excitons not between electron holes, but between fractionally charged quasi-particles, right? So what we want to do is to create 1/3 charged quasi-hole in one layer and negative 1/3 charged quasi-particle in the other layer and see if they form exciton. And to do this, right, let me first show you the Hall-bar data because it tells you the quantization, right? So we're working with the Hall-bar data. We're sweeping density along the equal density line, meaning that each layer filling is fixed to be the same, right? And the red data, the top channel is longitudinal resistance, bottom channel is Hall resistance. Red is measured from the drive layer, and blue is the passive drag layer, right? From the drive layer, you can see that you're getting all these plateaus. You get 1/3, 2/5, 3/7, right? And then 2/3 here, right? So the sequence look like a single layer state. The reason for that is because the interlayer separation, we intentionally make it very far away, about 7 nanometer, right? Almost double the value I showed you earlier. And we go to extremely large magnetic field so that the intralayer correlation is much stronger than interlayer correlation, right? And at the same time, right, for example, here you get Laughlin state in both layers. And if you look at the drag data, it's 0, right? Meaning that the two layers essentially decouple. But we do have 2 copies of Laughlin state. The drag is 0 because there's no quasi-particle in both layers, right? Because there's very robust charge gap of Laughlin state. And then what we're going to do is that we're going to start to try to create quasi-particle and quasi-hole just by doping it, right? We have a 1/3 Laughlin charge gap, and we can just change the Fermi surface to be 1/3 plus delta in one layer and 1/3 minus delta in the other layer, right? We're fixing the total filling to be 2/3, and we're essentially inducing layer imbalance so that we're creating the same number of quasi-particle and quasi-hole across the two layers, right? And so in a whole bar measurement, on the drive layer, you see this 1/3 plateau. Now we're changing delta nu as the x-axis, right? When we start to imbalance the two layers, at some point, the plateau disappears. But right around the time the plateau disappeared, this is drag data. There's a very large drag response, meaning that the two layers start to show correlation, right? Right around the time that you close the charge gap. So the whole this is a whole bar data. The Corbino data is a lot more definitive and indicative, right? So again, we're just changing layer imbalance at total filling of 2/3, right? The top panel is plotting parallel flow conductance that shows a very large range of insulating state, meaning that over this entire range, there's a very robust charge gap, right? But if you were to measure counterflow measurement, right, at the two ends of this range, the counterflow conductance is non-zero, while the parallel flow conductance is still zero, right? This shaded red region. And over this region, you can see a perfect drag response, right? Because we're still under the same charge gap of the Laughlin state, I think what happened here is that we're doping quasi-particle and quasi-hole into the two layer, and these quasi-particle just recombine to form exciton. So that in this region, the charge gap is actually contributed by the exciton formation, right? Right. You can actually test this in a number of different ways. I didn't put the data in here. For example, you can start from this point where there's a very robust charge gap and just warm up in temperature. And right around the time the charge gap closes, you also recover this perfect drag response, which means that, right, you can create quasi-particle, quasi-holes either by doping or by thermal activation. But regardless, once they're created, the first thing they do is that they recombine to form exciton. This exciton is interesting because that if you think about the braiding statistics, this exciton has fractional braiding statistics. So it's an anionic exciton.
It's not a boulder.
Right. So I guess Mike Zolotov and Ashwin had a proposal about neutral anionic superfluid of this type of exciton. My understanding is that the exciton condensed by you pair a few fractional exciton together to form a bosonic exciton, right? So the condensate is still a bosonic condensate, but the only difference is in the normal state. When you go through TC, right, the quasi-particle you get is, instead of a bosonic exciton, then they split back into the anionic exciton.
The condensate might look ability just ordinary exciton with one electron and one full.
Right. But the parent state is a fractional exciton. Right. That's my understanding.
Yeah, so the question has been keep emphasizing I think the exciton in the charge have closings.
Yeah.
But then what tremendous what state of going to observing, and that was another.
Oh, you mean
at what?
For this?
You start with that double box, what?
Right.
You clear.
Yeah. Right.
Final study practice and half gap each layer.
Okay. Right.
So then so by the racks what can.
Oh, so okay. So if you look at the Corbino measurement, when the exciton start to onset, the charge gap is still very robust. Right. So in this case, the exciton, this fractional exciton correspond to a incompressible state. What happened in the whole bar is that this, even though it shows interlayer correlation, this state is not fully developed. So when excitons start to appear, it's a compressible state. That's why it deviates from the plateau. Right. And there is a fundamental difference between Corbino and whole bar shape that we don't fully understand. although this difference exists for both this quantum hole bilayer and also monolayer. How the edge and the bulk interact probably is the key, right? The interaction in a way that's non-trivial and we don't fully understand. Okay, I have a little bit of time. Let me quickly talk about the third part of this talk, exciton solid, which is a work in progress, right? When over the years, there has been a lot of theoretical proposal, right? One of them is by Quinn here. The focus of all these theoretical discussion is that if you have a system exciton, right, it's a bosonic system, there should, in principle, be a crystalline phase of this bosonic system, meaning that exciton could form a solid, right? And the reason that the motivation for this discussion, of course, is because when you have a bosonic crystal at low enough temperature, there should be a superfluidity of bosonic solid. Right? This was proposed many, many years ago, 1974. Of course, that there has been experimental report of such super solid in helium, but later on we found out this is due to some artifact. Right? Nevertheless, a bosonic crystal that behaves like a superfluid is a very intriguing and seems like a paradox of idea, right? So controversial or intriguing that people actually wrote these articles, how solid is super solid. My understanding is that the supersolidity really happens for the vacancy in the crystal, right? When you have this super solid, the vacancy is free to jump around without dissipation. Right. So this is a very intriguing quantum matter of state, quantum state of matter, and the main challenge for us to realize it experimentally is that we just don't have so many bosonic state in solid state material, right? You need a bosonic state, and you need to get to the right condition for that to form a solid, and you need to probably want to be able to do transport measurement on it, right? So that you can detect this supersolidity. And a lot of the proposal that I just mentioned that argue that exciton should form a solid argues that you need to go into the dilute limit, meaning that the separation between excitons should become much larger than the radius of the exciton itself, right? And that kind of outlined the issue. If we put a quantum hole bilayer at 1/2 filling in both layers, right, the size of the exciton is defined by the magnetic length, right? And in this case, the separation between the exciton is also defined by magnetic length because you're at 1/2 filling, right? The separation is roughly 2 magnetic length. So in the past decades, we tried a lot to stabilize the exciton solid by changing interlayer separation or changing the magnetic field. In hindsight, we look back, we realize that we didn't do anything about this ratio, that, right? The ratio is always the same. Once we come to that conclusion, we realize that actually there is something that we can do to go to the dilute limit. And all we need to do is to create an imbalance between the two layers, right? So this is schematic. I'm plotting what happens when one layer is at 2/3 filling, the other layer is at 1/3 filling, right? In this case, you have 2 excitons, the interlayer separation becomes much larger compared to this case, right? You can push this to the more extreme regime that you can get to really dilute limit, right? And then, so that's what we did. And in the very dilute limit, there's a very interesting response, right? This is interlayer imbalance about -0.57. So it's already in the very dilute limit. I'm showing Corbino measurement result at total filling of 1, so still excitonic state, right? At the very low temperature, counterflow shows 0 conductance, parallel flow shows 0 conductance, right? It's an insulator. And what makes the insulator very intriguing is how it warms up. When it crosses a threshold of about 1 Kelvin, right? Parallel flow is still insulating. Counterflow start to develop non-zero resistance or non-zero conductance, right? And then if you do drag measurement, you realize that this, whatever insulator it is at low temperature, warms up into a state that looks like a superfluid, right? It exhibit all the superfluid signature. The issue is that this is a 2-terminal measurement, so we don't really know whether it's a normal fluid or a superfluid. So we go to a whole bar sample to double check, right? It's almost the same condition also in the imbalanced state. And at low enough temperature, this is not a exciton condensate. It has finite resistance, and the Hall drag deviates from the expected plateau, right? But as you warm up around 1.5 Kelvin, it warms up into a state that shows zero longitudinal resistance and the quantized drag, meaning that indeed we warm up into a superfluid, right? And when you go up higher in temperature, then everything starts to deviate, right? The drag also deviate, meaning that now you're starting to depair the excitons, right? So this actually raises a lot of really interesting questions. When we talk about bosonic condensate, we always assume that's the low temperature ground state, right? And this shows that there is a different low temperature ground state when under the right condition, right? When you cool down in temperature, you could hit a superfluid first, and then you hit another state that has a lower entropy than the superfluid state. So it's a question that at that time we asked that question to a lot of theorists. What can an insulator show lower entropy than the superfluid? Could that be a solid? And if that is a solid, could it be a super solid, right? That's kind of the work in progress here. We're asking a lot of questions. We're trying to think what kind of experiment we need to do. One, to confirm that it's a solid, and two, to see whether there's a super solid, right? The answer or the question kind of is staring at us right in the face. If you have a solid, it shows insulating behavior. That means the solid must be pinned, right? A super solid probably should not be pinned. You should see superfluid behavior. Then how do we know that this is a superfluid? What if this is already a super solid, right? So the question becomes fairly fundamental and very intriguing, and that's probably something that we're going to try to figure out in the next few years. Yeah, try to make progress in the next few years. I don't know if we'll ever figure this out. Okay, so I talked a lot, and I didn't really do much referencing, and so let me leave this page of a lot of the work we did over the years, and these are the reference that contains all the data I just showed. Of course, once I become faculty, for the first couple of years, I come back a lot. I try to come back as much as I could, and then I realized it started to become impossible. When some students are here, there are also students on campus that needs me, right? Also teaching and all that. So this is just to say that the credit goes to the student who get to come to the MagLab and do the exciting physics. Most of the work here is done by James and Ram. They form a really nice team and supported by our theoretical colleagues and other students in the group. We're supported by Air Force and SF, but most importantly by MagLab for allowing us to use these state-of-the-art magnet, right? So it's great to be here. Thank you for listening to this talk. And if you have questions, I'll answer them.